exponential functions in preparation for your end of course test in Algebra 1. We just want to remind you of the functions you've already studied. Linear functions are of the type y equals mx plus b. Notice x is to the first power in that linear function, and you've looked at quadratic functions where you have ax squared plus bx plus c, where now you have a squared on the x. We're going to now take a look at exponential functions. In exponential functions, you have a variable as your exponent. This is the growth function. This will need to be memorized eventually, where your final amount is equal to your initial amount times a growth rate or growth factor of 1 plus the rate raised to a power. So over and over again, you are multiplying your initial amount. And so exponentials tend to get large fairly quickly. Once again, a sub 0 stands for the initial amount, what you begin with, how much money or how many fish, etc. A is your final amount. 1 plus r is called the rate factor. That's what actually gets multiplied each time. The r itself is the rate of increase. It's usually given as a percent. It must be in decimal form in your formula or your equation. T stands for your number of time periods. That's exponential growth. Notice exponential decay is almost the same. The only difference is it's 1 minus r. So this is less than 1. So every time you multiply, you'll be decreasing your amount. But again, all the same variables apply. A sub 0, initial amount. A, final amount. The factor that you're multiplying by is the 1 minus r. The r itself in this case will stand for a rate of decrease. Once again, use decimals, please. T is your number of time periods. Note, however, that other variables can be used as well. Follow directions on the EOC. They'll tell you what to use. They most often use x and y, or sometimes they'll use function form. So instead of having a sub 0 and a here, they'll use y and x for the exponent instead of a t. Or they may use f of x for the final amount, still using x as your exponent for time periods. Just want to remind you of the shapes of these graphs in case that comes up. Linear graphs are straight lines. Quadratics are your parabolas with the U shape. Here's your first look perhaps at the exponentials. Exponential growth starts out slow and then grows very rapidly. It's always increasing. Exponential decay tends to decrease rapidly in the beginning and then tends to level off. This reminds me a lot of a car depreciating after a period of time. Here's some sample problems. This is exponential growth. The number of fish in a pond increases at a rate of 4% per year. If the pond began with 1,000 fish, set up an equation to find the number of fish after 8 years. So, of course, we know it's growth because it's a title and because it says it's increasing at 4% per year. So 4% written as a decimal is 0.04. The beginning amount was 1,000. They said they began with 1,000 fish. We're checking the pond after 8 years, so we're missing our final amount. So here we go. This is where we place them. Beginning amount here, multiplied by the parentheses of 1 plus 0.04 raised to the 8th power. If you want, you can go ahead and add that up, and it'll look like 1.04 to the 8th. So far on the EOC practice and on what we've seen, they don't ask you to solve it. They just ask you to be able to set up the equations and understand what they mean. Here's another sample. Each year, a company spends 110% of what it spent the prior year. In 4 years, the spending will reach $117,128. Set up an equation to find out how much is spent this year. What is the rate of increase? So we don't know what we're beginning with, but we have the final amount after 4 years of $117,128, so that goes over here. 1 plus r is given as 110% already. So as a decimal, that's 1.10. So that makes the rate of increase 10%, or 0.1. So we have the final amount. Here's the beginning amount that's missing. Here's our 1.110 and 4th power. A final growth example. Every hour, the amount of bacteria in a culture doubles. If there are 4,000 bacteria to start, set up an equation to find y, the number present after 12 hours. Notice these double each hour. And the time periods can vary from hours to years, months, etc. It does say you started with 4,000 bacteria. That goes here. For doubling, they're giving you the growth. That's the whole growth factor. It's a doubling, so just 2 goes there, which is actually technically a 100% increase. But I wouldn't worry about that so much as just getting the 2 inside the parentheses. And we were going to do 12 hours. So this is a setup for that one. Let's look at a couple decay examples. Each year, a teacher loses 6% of her counters. She started this year with 1,200 counters. Set up an equation to find out how many she will have left after 3 years. So again, her beginning amount is 1,200 counters. That goes here in the front of the parentheses on the right side. We don't have the final amount. We're leaving that as an A. Her rate of decrease is 0.06. That gets subtracted from 1. If you go ahead and do the subtraction, that'll be 0.94. So you see this is less than 1. That's why it's going down or decaying. And we've got our 3 years. Maybe she can retire without buying new counters. Here's a sample 2 for exponential decay. Every minute, half of a radioactive substance decays. If there are 800 grams left after 10 minutes, set up an equation to find the number of grams used in the beginning of the lab. So this is every minute, half of a radioactive substance decays. That means our decay factor, our whole 1 minus r, is a half. Notice if you take 1 minus a half, you get a half. Very convenient. We don't have our beginning amount. Here's our decay factor. We're going to have half left. We're going to do this for 10 minutes, and we result in 800. So this is a setup that will help us find how much we started with. Sample 3, our last exponential decay function sample. If a car depreciates at a rate of 9% per year, set up an equation that finds the number of years, x, that it takes a new car costing $35,200 to depreciate to about $20,000. So this is decay. We started our car, our brand new car was worth $35,200. Then at the end of this period, it's worth $20,000. The rate of decay was 9%, which as a decimal is 0.09. I went ahead and subtracted here. 1 minus 0.09 gives me 0.91 as my decay factor. And of course, my time period is unknown, so I put in an X. It told me to use X, so I'm following directions, not putting a T there. Notice the difference between the exponential growth and decay. In growth, the rate factor is greater than 1, and the initial value is less than the final value. The rate of increase is found by subtracting 1 from the rate factor. In decay, the rate factor is less than 1, and the initial value is greater than the final value. The rate of decrease is found by subtracting the rate factor from 1. Here's some practice for you. Growth or decay, name the rate of increase or decrease. You could also name the growth factor or decay factor. Number 1 is y equals 300,000 times quantity 1.06, all raised to the x power. Number 2, f of x equals 75,000 times quantity 0.87 raised to the x power. Third one, 3,200 equals 5,000 times quantity 0.8 raised to the t. And number 4, a equals 48,000 times quantity 1.24 raised to the 6th. The next slide can check your answers if you're not sure. Number 1 should be growth because this factor here is greater than 1. And the rate of increase would be 0.06, which is 6%. The entire 1.06 is called the growth factor. In number 2, we should call this decay because our factor is 0.87, less than 1. If you subtract 0.87 from whole 1, you get 0.13, which would be a decay factor of 13%. Number 3 is also decay. You can tell two ways. The final amount is less than the beginning amount, plus our decay factor is 0.8, which is less than 1. Again, subtracting 0.8 from 1 would give me a decay rate of 20%, 0.2 or 20%. Number 4 should be exponential growth, because again, our factor here is greater than 1, 0.24 much greater than 1, which means a 24% rate of increase. And you can double check, those are the answers. Here's the EOC practice. These are actual sample problems that they have on the state website. A scientist is studying wildlife. She estimates the population of bats in her state to be 270,000. She predicts the population to grow at an average annual rate of 2.9%. Using the scientist's prediction, create an equation that models the population of bats, called Y, after X years. So we must use Y and X to be correct. We'll have you check your answer in a couple slides. Here's our next practice. A landscaper puts 5 fish into a new pond. The number of fish doubles each month over a period of time. Write a function f of x to model the number of fish in the pond after x months. Again, we can check your answer. Here's our third and final practice question. The population of rabbits on an island doubles every year. On January 1st, the population is 150 rabbits. Which equation can be used to find the number of years, x, it will take for the population to reach 4,800? So this is doubling every year. That would be a growth. I think, though, I don't think any of our answers indicate decay. But recall, proper setup, you need to take the beginning amount times your growth factor, and the growth factor is raised to that power. This is not so because you're adding and you don't have any exponent of x. This is a 2x. B, you have your exponent on the wrong thing. You have your exponent on the beginning amount, not on the growth factor of 2. C, you have the exponent on your growth factor of 2, but you're adding the 150. D is the correct answer. It's 150 multiplied by the growth rate or growth factor of 2 raised to the power. So since this is our final one, our answer to this one is D. We can also check our answers to the other 2 samples. 270,000 was the beginning amount, and it was increasing at 2.9%, which is 0 or 0.029 as a decimal added on to 1. And in number 2, they said use f of x. I think on the test they had the f of x in there for you. 5 fish to begin. They were doubling, so that's your factor of 2 raised to the power of x. And we already discussed number 3. Hints. Please make sure you memorize and understand the setup for these exponential equations. They will appear on your EOC. There were 3 of them, just on the practice test alone. Brightspace teaches these exponentials in the last block. You may need this tutorial because the test is in April. Call LDA for an appointment if you need further help. Good luck.